I'm obsessed with Enceladus. It is this world here in the solar system where you've got obviously some kind of ocean of liquid water, and yet this ocean is being sprayed out into space, waiting for us to sample it. All we have to do is just fly through that plume of material with a mass spectrometer or two and try to see if we can detect any kind of organic elements, compounds, the building blocks of life, or maybe even life itself. It would be an amazing scientific boon if we could do that. But Enceladus is orbiting Saturn. It's very far away. It's going to take the better part of a decade to get out there. Is there a way to get there faster, cheaper? My guest today is Dr. Manasvi Lingam, and he has been thinking about this problem and many other problems. And he's quite intrigued about the idea of using light sails, not to fly out to other star systems, although he is also thinking about that, but as a way that we could explore really interesting places here in the solar system with radically different spacecraft, spend more on the infrastructure to accelerate your spacecraft, and that allows you to send more lightweight spacecraft at higher speeds to check out places. And maybe this could be the ideal way to explore a world like Europa or Enceladus or Triton. So we have a long-ranging conversation. We talk about this mission, but I think it's really important for you to understand just how wide-ranging and like how into so many different fields Manasvi is. He talks about astrobiology. He has a background in engineering. He has a background in physics, in astrophysics. He can sort of do everything and anything. And so if you need somebody to calculate your fusion drive, he can do it. If you need someone to find the amount of rogue planets out there, he's your guy. And so we spend, like I said, about half the conversation just talking about Europa, Enceladus, light sails, but then we just keep moving and we talk about rogue planets and other ideas. What is the smallest possible life form and the other kinds of things that he's obsessed with. So enjoy this fascinating conversation with Manasvi Lingam. Manasvi, why is Enceladus such a fascinating world to you?
Yeah. Thank you for that question. And just to begin with, I just wanted to say I'm a big fan of Universe Today and especially your work on the YouTube channel as well, Fraser. So it's great to be on your channel. Now coming back to Enceladus, it's a fascinating moon because for a long time, as we all know, a small moon of Saturn, which is about 250 kilometers, I believe, in terms of its radius. And one of the most fascinating things about that moon is it's so tiny, yet it happens to have an extremely deep ocean that is underneath its icy shell. And it's really fascinating because the average depth of Earth's oceans is about 3 kilometers, whereas Enceladus may have an ocean that is 10 times deeper, despite being such a tiny moon. And the best part of it all, from the standpoint of an astrobiologist, is that it has this big plume of material that is erupting from the surface, which is believed to originate from that subsurface ocean we have talked about. And so what this means is that there is an unprecedented opportunity to sample the plume and then to look for materials in its surface, on its surface and in its interior.
Now, the NASA, as part of the planetary science community, as part of their last decadal survey, went through all of their priorities and highlighted that, yes, indeed, Enceladus is one of the most interesting places and that it's a high priority. And yet we're seeing the issues with, like, the budgeting issues with the Mars Sample Return mission, some other budget cuts at JPL, like money is a little tight these days. So you're proposing a way potentially that we could get samples, either study them locally or return them, hopefully in a feasible shorter term process. So what are you proposing?
Yeah, great. Thank you. Yeah, indeed. As you said, there is a funding crunch everywhere. And so I want to, before I tell you the solution that my collaborators and I, who are Adam Hibbard of the Institute for Interstellar Studies and Andreas Hein, who is a professor at the University of Luxembourg, worked on. I want to tell you a little bit, I want to remind the viewer A little bit about space exploration. We all know that it began in 1957 with the launch of Sputnik. And of course, the first interplanetary missions were in the early 1960s. And we've relied on chemical propulsion for 60 years. And it's done great. I mean, it's been the bedrock of our space exploration. But then the question then comes up, at some point, either now or in the future, are we going to hit some kind of a barrier insofar as chemical propulsion is concerned, mostly because of the fact that a rocket has to carry a huge amount of fuel to undertake complex orbital maneuvers, especially to pursue deep space exploration of the outer solar system. And this is something that we are increasingly running into more as we start to encounter intriguing targets in the outer solar system. So, what my colleagues and I have been really interested in is harnessing the potential of light sails, which I will describe in a second, and using them to carry out interplanetary exploration, perhaps on a scale that has not been achieved so far. And so now coming to light sails, what are light sails? As the name indicates, they are essentially spacecraft that are propelled by light. Just as a sailboat is propelled by wind, so too does light have energy and momentum associated with it. And some of that momentum can be imparted to a spacecraft, thereby accelerating it to a certain speed. And it turns out that if you use laser, you can focus a lot of energy and momentum onto a relatively small area and thereby enable the sail to achieve high speed. And this is, of course, a principle that is also very old, but it is only in recent times that it has seen renewed interest thanks to some concepts such as the breakthrough Starshot mission and so on.
Right. And people are so obsessed about using this technology to go to other stars, but you're proposing let's use this as a way to explore the solar system first.
Exactly. To use the well-known metaphor, one must learn to walk before one can run. And so what we are really interested in is demonstrating the potentiality of light sails to revolutionize our exploration of the solar system. Because if we can do that, that would be beneficial in two ways. One, space exploration of the solar system is something that can be valuable in its own right, especially given that there are many abodes in the solar system that might harbor life. And secondly, the other really interesting thing is that if we can demonstrate that, yes, light sails are well suited for planetary exploration within the solar system, that would increase confidence in either governmental agencies or private agencies that, yes, we can actually now perhaps start to think about extending it to interstellar scales as well. So therefore, I think starting with these kind of precursors would make the light sail architecture both more viable as well as more exciting as far as delivering short-term benefits is concerned.
All right. Well, so I guess there's sort of two parts to this process then. First, let's talk about the propulsion side of things, and then we'll talk about the actual science that we could do. So let's imagine that you've made the case that this mission is going to fly. What would it look like? How would it sort of function and operate? Where would the lasers be? What would be the various pieces of the puzzle that would bring this thing together?
Yeah, so there's still a lot of things that need to be worked out. One of the most important among them, which you've rightly highlighted, is the laser. Because, again, for interstellar propulsion, what was required was something on the order of 10 gigawatts of energy or so, which is a huge amount of energy. Whereas what is required for an interplanetary mission to Europa's moon, to Europa, which is Jupiter's moon, or Enceladus, is that you would only, quote unquote, only require about merely require only 100 megawatts of power. So then that brings up the question: how would you, of course, supply so much power through laser? Now, some of the most powerful continuous wave lasers can provide a power of about 100 kilowatts, which is 1,000 times lower than the stipulated amount of 100 megawatts. So what you would need is about 1,000 such lasers acting in tandem and using things like adaptive optics and so on to achieve, synchronization, to achieve coherency, and so on, and then focus all of that light energy onto the sail. So that is still something, which is still somewhat far from being developed. But as we can perhaps discuss later, the timeline that we foresee is not that this would be done in a few years, but in a couple of decades. So based on how laser technology and advances in adaptive optics are going, I think that in 20 years, it should not be an inconceivable thing to do, and should not even perhaps be an impractical thing to do.
So you see, on the one hand, the increasing power of the lasers and the science moving forward, and then on the other side, thinking about how you could array a whole bunch of lasers together at the same time in some location to build up the shortfall. And I mean, this is a basic piece of infrastructure. Once you have this laser array available to planet Earth, then Europa, Enceladus, these spacecraft are almost free at this point. It's the laser that's the expensive part.
Yes, exactly. First, building the infrastructure, and then secondly, taking into account that you would, of course, expend a lot of energy per launch. So there's certainly some launch cost associated with it. But yeah, once you have your infrastructure, you could start to utilize it many a time. So in some sense, although a very loose analogy, one might be reminded of reusable rockets, that you have this infrastructure that can be used over and over without necessarily building a lot of things from scratch. Of course, the light sails themselves have to be built from scratch. But if you find a way to supply the power, then you just keep beaming multiple spacecraft into space. And indeed, one of the things that we looked at was the viability of a swarm of small light sails, each carrying a CubeSat that could carry out a synchronized exploration of some of the potential astrobiological targets in the solar system.
And so would this laser array, would it be ground-based or space-based, do you think?
Yeah, that's a really good question. So, of course, if one were to have it in space, there would certainly be some advantages insofar as, not affecting the atmosphere would be concerned, insofar as not having to worry about transmission through the atmosphere. But then, again, putting such a big system in space might not be practical for, because you would still have to launch it into space using conventional propulsion, such as, say, chemical propulsion. So what we looked at was the possibility of having this laser array on Earth, and depending on which moon we would be targeting, we looked at different locations. One of the things we found was that as far as, say, Enceladus is concerned, having the light sail architecture and the laser array be somewhere near the Arctic Circle or the Antarctic Circle, about 60 degrees north or south, might be one possible location.
And that just gives you better geometry for being able to access some of these outer regions of the solar system?
Yeah, exactly. So you get better launch windows for achieving the kind of encounter speeds with Europa and or Enceladus that we would want. So that's certainly one of the things. Yes. So it's really all about optimizing the trajectory such that you achieve the desired encounter velocity at the point when the light sail intercepts the plumes of Enceladus, or perhaps even the potential plumes of Europa, which have been ambiguously detected.
Right. Okay, so we set up this laser array, and it's a huge undertaking by humanity, but now we've got this array in place and we're learning how to use these lasers. A rocket launches, it has the probe or maybe a swarm of probes that it deploys into orbit, and then they're accelerated one by one by the laser array out into their direction.
Yeah, exactly. So we looked at two different possibilities, one of which was using just a single light sail, but with a fairly substantial payload of, the scientific payload was, and including some of the associated subsystems needed, such as power, communications, and so on, would be about 100 kilograms. So that was one we studied where the total payload is 100 kilograms, and then you have a light sail that carries this payload to the icy moon. The other one, which we looked at, where you would be, of course, much more constrained in terms of instrumentation, would be to have a swarm of hundreds of these light sails, each carrying a payload of a kilogram or thereabouts.
Mm. Oh, wow. Okay. All right. So now let's talk about the science. So, it's one thing to get these probes out there. Oh, and I guess how long would it take? How long would it take to get to Europa versus Enceladus?
Yeah, that's a great question. So again, of course, we were looking at some criteria, like trying to optimize the encounter velocity so as to maximize our science return. So what we found is that in the case of Europa, you would be able to reach it in a time scale of 1 to 4 years, whereas in the case of Enceladus, you could reach it, really fast. And then you could reach it for Enceladus in a time scale of 3 to 6 years. Now, here I should actually add that because of the power of light sails being what it is, you could reach it extremely fast. For example, if you look at the relativistic light sails proposed by Breakthrough Starshot, you could, of course, get to these moons in a span of days. But here we were actually trying to optimize the science, as we will talk about later. But it's still a few years, which is great because, as we know, many of the conventional missions are about 10 years, a little bit less, a little bit more. Whereas here you can cut down that time by anywhere from a factor of, say, 5 to a factor of 2 or 3.
Right. All right. So let's talk about that science. So what kind of science would you hope to do as you reach, let's say, Enceladus?
Coming to Enceladus, like I said, it's definitely guaranteed that there's a big plume of materials coming from the surface, which is believed to be sourced from the underlying ocean. But then this brings up the question, is there life in that ocean? Could it be just simple microbes, or perhaps there's even fish that are swimming, in Enceladus ocean? Obviously, we don't know. And the latter seems to be somewhat unrealistic on energetic ground. But now let's stick to microbes for the time being. So then the question becomes, how do we detect signatures of life that are present in that plume? And one of the strategies that scientists often use is to search for some of the building blocks that make up life, things like amino acids, things like nucleobases, which are one of the components of RNA and DNA, lipids, which make up cell membranes, all these kinds of molecules. Now, none of them in isolation is enough to assure the presence of life, but it certainly gives us some confidence that at least the environment is habitable and perhaps even inhabited. So what we set out to do was to look at the current instrumentation available. And so it turns out that we have this particular type of instrument known as mass spectrometers, and in particular, there's a subclass of them. What they allow you to do is to determine the chemical composition of a species, of a chemical species. And so what we did was we looked at this existing instrumentation, and then we also asked ourselves at what velocities would the spacecraft need to encounter the plume in order to detect these molecules? Because here's the thing, if you go too fast, the molecules are going to impact the spacecraft at very high velocities as seen from the perspective of the spacecraft. It'll feel like the molecules are just coming in and bumping into you. And so that's not a good thing, because if they crash into the spacecraft at too high a velocity, then they just get disrupted, and which is something that we don't want. So what we suggested instead was we want to minimize the encounter velocity as much as possible, so that you move to an optimal range where you can probe these plume for the biosignatures. And what people have shown, a lot of planetary science literature that has been done has shown that encounter velocities of 4 to 6 kilometers per second with the plume are desirable. And what we found was that even without having any onboard propulsion to slow down, you could still, just by sending a light sail passively, you could achieve an encounter velocity of 6 kilometers per second, which is really close to that optimal encounter speed I mentioned. So to wrap everything up, we would like to use this tool called a mass spectrometer, and then the goal would be to try and find biomolecular building blocks such as these amino acids, nucleobases, lipids, and so on, and with the appropriate encounter velocity.
And so that flight time, that 3 to 6 years flight time, that's not as fast as you could go. That's more about making sure you slow down enough that when you do your flyby, you're not destroying the molecules. I did a recent interview on this subject, sort of talking about different speeds. And it's like, if you want big, like bacteria, there are limits to the speed of being able to detect bacteria. Otherwise, you start to splat them on your windscreen. And so, is there like a slowest speed that you would want to go if you wanted to see something big and more interesting?
Yeah, so that's a really good question. It turns out that with the more passive sort of, flyby, where you're just passing through the plume and you don't have any other onboard, propulsion system for slowing down or executing other orbital maneuvers. Without that, you get to about 6 kilometers per second, but going much slower was not very feasible. But yes, to answer your question, there have been some suggestions that if you go at speeds of less than 4 kilometers per second, some of the techniques actually rely on fragmenting the larger molecule into smaller parts and then analyzing the smaller parts and then putting back the data together. It's sort of like, like Lego, where you can not only build up from the block, but you can also tear it down and construct something else. So the suggestion is that the lower bound might be, somewhere in the range of 2, 3, 4 kilometers per second.
It's interesting. Sort of imagine, do you want to be able to gently collect the samples as you're passing through, or is it more like throwing them into a blender and just the speed that you go will define that? The balance is always between, is there a way to do a sample return mission, or does it have to be in situ? And it feels like, if you're going to try to bring along a mass spectrometer, try to do some, what's the minimum size of that mission to carry along enough science to be able to get a definitive answer to your question?
Yeah, so I think with the technology we have, like I said, a total 100 kilogram payload, which includes things like, a high gain antenna, things like having the radioisotope generators to do some internal, to power some of the internal systems, and then also to have the mass spectrometer, which would be similar to the one on Europa Clipper, which is called SUDA, Surface Dust Analyzer. When you put all of those together, and you also, of course, allow for some tolerance levels and maybe some other systems that I didn't allude to, I think about 100 kilograms, especially when we are talking about 20 years from now, should be doable. Now, that being said, it is somewhat hard to predict the pace of miniaturization. So the 100 kilogram estimate, I think, is a fairly conservative one that, would be certainly achievable 20 years from now. But moving to the other extreme of swarms and then using these CubeSats, well, right now we certainly don't have a mass spectrometer that I'm aware of which can recognize these biomolecules, which is less than a kilogram. And then when you add in all the other auxiliary systems, I'm not sure you can do it in, say, a kilogram at the moment. But 20 years from now, again, it's rather hard to focus, which is why, we accounted for one more conservative scenario where with a 100 kilogram payload, you would be able to incorporate all the salient subsystems. But then we also looked at the somewhat futuristic pathway whereby maybe you can use a 1 kilogram payload to to incorporate all the instrumentation you need. And another advantage of the swarm, of course, it has a lot of redundancy built in, B, and a lot of flexibility built in as well, because you can have different probes with different payloads, which can be complementary or supplementary to each other.
So, I mean, this idea of, say, 100-kilogram spacecraft, I mean, you're proposing the light sail idea, but couldn't you also put this spacecraft on top of a Falcon Heavy, plan a couple of planetary flybys past Jupiter, maybe to build up a little bit more velocity and pull off the same mission, and maybe even have a way to go into orbit or be able to stick around longer?
Yeah, that's a great question. So I have two answers for that. Both are important, but in different ways. The first thing I will say is one of the things we also study in the paper, and perhaps it can be linked in the description somewhere, is that we do talk about the possibility of having onboard propulsion as well. So it would be primarily a light sail, but with some amount of onboard fuel for maneuvering as well. So that would indeed allow for some kind of further maneuvers involving Jupiter or Saturn, and also perhaps just slowing down and trying to get into orbit so that you do multiple flybys, and you can even perhaps have an orbiter in the extreme case. So we do certainly look at those hybrid architectures, as one could call them, which have both the light sail component as well as the chemical propulsion component. That's one answer I would offer. And the second one is, I would say, even if it were to be true that chemical propulsion, is the way to go for Enceladus, if we go to something like, say, 500 AU or 100 AU, some hundreds of AU, of course, right now there's no interesting target we have found, although there are some ideas that Planet 9, if it exists, may be prevalent there. It turns out,
I mean, there's always the solar gravitational lens.
Course,
I mean,
exactly,
there's
exactly,
right?
Yeah. That's a very good point. Yeah, exactly. The FGL is one more crucial and documented piece of, it's a location that is certainly there. So for all of those, it turns out that at least with the current rockets we have, you're not going to be able to get there, with the mass ratio one has, the requisite delta V requirement will not be met unless you probably do an endless number of slingshots. So there are certainly limits up to which chemical propulsion can operate. So this sort of harkens back to my original point that we see this as a precursor, and if it were to materialize, that it would show the world, well, look, light sails can also assist humanity in understanding our solar system better and in exploring the deep space around us. So I think in that regard also, it could be a great demonstration, in which case one could use it to venture out further and further out into the solar system. So, at 500 AU, you could have the solar gravitational lens. At about 1,000 AU, the Oort cloud would start, and some of the other work we have done in the last year entails, looking at potentially free-floating planets just wandering through the solar system. So all of these, I think, are targets that are not accessible to chemical propulsion, but light sail architectures could enable us to explore these worlds, and Enceladus and Europa could be the first step in what could be a very rich and rewarding journey.
But it feels to me, and this is your specialty, but it feels to me like Europa and Enceladus are like phase 2 kinds of targets that would require, as you said, maybe 100 lasers kicking in, each one in the multi-megawatt range to be able to work together to form this array. I mean, that's a serious piece of infrastructure that's going to have to be built, not to mention the political issues about who gets to own it and where it gets pointed and so on. Like, this idea of sending these light sails is so exciting at the smallest scale. I mean, is there what would be sort of like the smallest interesting mission that you can imagine with this kind of technology? I mean, could you send these tiny 20-gram sails to do flybys of asteroids and take pictures and things like that with a smaller laser and a smaller spacecraft?
Yeah, that's a great question. So, we did indeed, of course, because it's projected 20 years into the future, we do implicitly assume, a few assumptions, which I think can and should be, of course, questioned, which does include things like, humanity having a relatively stable society, that is still investing in science and so on. So, it goes back to the geopolitical implications you said. It also assumes that we have some technical mastery already over light sail architecture. So, this is where I think your question would come in. So, Europa and Enceladus are about 5 to 10 AU away from Earth. Depends on the exact number. I mean, the configuration of the various planets, Earth, and these objects. But I think one cannot certainly right away do those missions. So I think it does. I do agree with you that one should start even smaller. Maybe with a megawatt scale laser array instead of 100 megawatts, where you send a very lightweight probe to a near Earth asteroid, maybe zero point 0.1 AU away or about 1 AU away. Just again do a proof of concept. Then perhaps the next step would be to do a flyby of the moon, then Mars, then lots of other objects along the way. So yeah, I think it has to be very much step by step. And as for what the lowest mass should be, again, Breakthrough Starshot famously looked at gram mass probe, and certainly those seem to be feasible. But that being said, of course, they can't do a huge amount of science because of their power requirements, because of their size requirements as well, and because certainly you would not be able to carry things like mass spectrometers at those masses. So yeah, I think it really depends on the kind of science you want to do. But if it's just imaging, you want to put a camera, yeah, that absolutely could be done with a gram mass
Yeah.
spacecraft. And yeah, you could start off really small and explore near Earth asteroids, and then from there you could go on to look at moon and so on.
I mean, there was an idea that I liked, this idea of electric sails. I don't know if I'm sure
Mm-hmm.
you've looked into electric sails as well.
Mm-hmm.
And there was this proposal that you would launch a fleet of these tiny little
Mm-hmm.
electric sail spacecraft,
Mm-hmm.
and then they would fly out
Yeah.
on orbits
Mm-hmm.
that would fly out to say 10 100 different asteroids, but then the key is like you wouldn't be able to communicate with them, but instead you would wait for them to fall back down into the inner solar system, get close to the Earth, and then you could communicate. So that, I think, then you have that advantage. Like, you don't need as much laser power because you don't want to send them at high velocity. You want them to fall back to you, and then you're asking yourself, like, what could you have a Falcon Heavy that has a 10 kilowatt laser on board that then throws out a whole bunch of little mini probes around it and just starts accelerating them away one at a time to sort of test out the technology. I mean, it feels to me like there is this giant gap in practicality right now, that you're seeing these presentations from Breakthrough Starshot. I'm reading papers from people like you and a lot of people in this field, Marshall Eubanks, who
Yeah.
I've
Yeah.
interviewed many times. He's one of your
Of course.
collaborators.
Of course.
That there's all this hand waving about that technology, but where does it start? Like, if we know that the age of light sails has begun, what does that first, and knowing that you're going to need that infrastructure of the laser system, what do you think is like the first practical kinds of demonstrations of this technology that we could probably see? Because I don't think you said, well, first we have to spend $1 trillion building a laser array that we don't know if it's going to work. That doesn't seem feasible to me.
Right. Yeah, no, that's a great point, and I think certainly, a lot. As I said, these proposals do assume a lot of maturity in light sail technology as the starting point, and that is indeed one of the things that I think is, to want of a better word, is a limitation of all these papers. And so, what I would say is that, yeah, by the way, I do love electric sails as well. And as you said, I have written a couple of papers on them too. Yeah, but coming back to light sails, I think, yeah, we should probably start even putting aside near Earth asteroids. There's still things we don't know about Earth's magnetosphere very well, or say, to pick a more specific example, maybe the magnetopause or the magnetotail. I mean, various components of Earth's magnetosphere. So that is, of course, just something like 10 Earth radii, so it's much closer than the moon. So I think even exploring that and then getting some insights would be valuable, especially if you have a swarm of these probes. Then you could sort of surround many different areas of Earth's magnetosphere and then map out a three-dimensional structure better than having a single spacecraft trying to trace out the outlines of the magnetosphere. So I think these kind of missions, would be of course very valuable, not just for planetary astronomers or astrobiologists, but for planetary scientists, space scientists, and so on. And for that, again, depending on the mass of the probe, maybe you could get away with something that's a megawatt or less. And for that, you would only need, a few tens of, let's say, 10 kilowatt lasers that would be needed. And to achieve coherency and precision in terms of synchronizing those tens of lasers should be doable. I mean, I think right now the record, seems to be about a dozen or so. It's not exactly my area of expertise. So I think that, yeah, that's where one would start. And obviously, even that would still be a fairly expensive mission. One would still obviously be talking in the millions, and the laser infrastructure would be on the order of $1 billion, to begin with. But certainly not $1 trillion, as some of the more ambitious proposals demand. And so I think one would want to scale everything up by a factor of 10. So let's say $1 billion in total capital expenditure, 10 lasers. Then the next step would be 10 billion, 100 lasers. And so kind of to keep adding to an infrastructure that's already there rather than building many different outposts. Like choose one location which would be convenient from a geopolitical standpoint, ethical standpoint, technical standpoint of having good launch windows, good atmospheric conditions, and then kind of keep building it brick by brick. That's how I might envision it, but then this is also, of course, somewhat speculative.
Yeah, I mean, I think about the world of AI right now, that once this idea of large language models were developed and we saw the power of these things like ChatGPT-2 and eventually ChatGPT-3 and ChatGPT-4, suddenly people realize there's ways to make money from this, and then there's an investment and it's incremental. And, say ChatGPT costs $5 million to train, and then GPT-4 is on the order of 100 million or 50 million. And then now we're seeing they're starting to pull together budgets that are going to have some of these training runs cost into the billions, tens of billions. They're piling on the computers. And so it's like you need this transition from the and that it's such a heavy infrastructure cost. It's really hard to figure out how you get there from here, because it we all learned about Breakthrough Starshot. I feel like it's 10 years ago when they made their announcement. I'm not sure how long it was that they made their announcement. And there's been a lot of great ideas. You guys have been producing a lot of documents, a lot of papers, but a lot of it is like question mark, question mark, question mark, like multi-trillion-dollar laser array goes here. And yeah, absolutely, there are new materials that need to be developed and so on. I'd like to shift gears now and just talk about your process, because I highly recommend you go look at Manasvi's like list of papers on Google Scholar. And for people who enjoy my channel, the kinds of topics that I focus on, each one of these is catnip to people. You're proposing deep space missions, sample return missions from Proxima Centauri. You are willing to think some pretty out of the box ideas and do the math. Where does this come from?
Yeah, that's a great question. I think, it's just sort of nice to have an answer that would be somewhat unorthodox, but I think I have the most boring answer ever, which is probably it goes back to Carl Sagan to some degree.
Yeah.
A lot of my family members, my parents and so on, my grandparents too, actually, were all big fans of Carl Sagan, especially his Cosmos series, which aired, in the early 1980s. It was before my time, but I grew up on stories about it and so on. So I think it definitely, put that spark in me. And of course, having had a bit of a meandering academic life has sort of helped because you pull in different skills at different points in your life. I mean, my undergrad was in engineering, the PhD was in physics, postdoctoral appointments were in astronomy, applied math. So I think all of these have contributed something or the other. And yeah, I think insofar as exploring unorthodox ideas, of course, on the one hand, it's really fun to do, but on the other hand, one wants to stay as grounded as possible. So that's been obviously a challenging thing to do. And so yeah, it's still something that trying to figure out every day.
It's interesting though, right? You've got the first piece of the puzzle is engineering.
Right.
And then the second piece of the puzzle is the astronomy and astrophysics and so on, that you're sort of rooting those ideas in a more practical, okay, but is this going to really work? So like, what's your process like? Like, do you have these shower thoughts? Or are you just like driving in the car and you're like, I wonder what it would take to dismantle Mercury and turn it into a Dyson sphere or whatever, right?
Yeah.
And for most people, I think they have a filter where they go, that's ridiculous. But you clearly take these ideas one step further.
Yeah, no, I think it's sort of, a lot of them do indeed come in places like the shower or when one is washing dishes. I like to wash dishes by hand. I've never used a dishwasher.
All right, you're a crazy person now. I take it all back.
Yeah, so, it's kind of interesting place to get ideas. But then I think to the second part of your question, I would say some part of my work has been very conventional. I started off in plasma physics and doing pretty conventional things about, say, magnetic reconnection, which is documented in the magnetosphere, which we were talking about, things like that. I still, do some fairly standard work. For instance, I've done fair amount of work on atmospheric escape from exoplanets, which again you involve using a lot of plasma physics. But these in more, I would say, innovative or out there ideas also are part of the whole corpus. And so I think it's having both has helped because these more grounded works help keep the more speculative works a bit more grounded as well. And then these more imaginative works help add a creative element to the more routine work as well. So I think they all feed off each other. So I think it's that synergy that really works.
So, I mean, can you give me an example of an idea, maybe one that you've had recently, where you're like, I wonder if this is possible, and then because you don't like your instincts don't tell you immediately that this idea is feasible or not, and then you sit down and you're like, nope, this will never work.
Yeah.
So like most people, they have instincts where they say, like in their mind, they say, why don't they just? And then they say something like, why don't they just, I don't know. And the classic example I always get is like, why don't you just have the Ingenuity helicopter fly over top of a rover to blast off the sand, and then that'll clear off the dust. Why don't they have a little fan that they blow onto it, whatever? And so I think that this future that we have can go in so many different directions. And as you sort of are creatively looking at these different pieces and you're putting them together in your mind, new outcomes are coming. And so at some point you kind of go, I wonder if that would work. And then you sit down and you do the math and you're like, nope, that's ridiculous. Have you had one of those recently?
Yeah, I think in a sense, although it was not completely in the engineering realm and a bit more in the science realm, was the following. So, the popular narrative is that Proxima Centauri is the closest extrasolar planet to Earth. I mean, it's repeated so often that, we take it for granted. And yeah, it makes sense why people say that, because Proxima Centauri is the closest star to Earth. And we are implicitly brought up to believe that planets exist around stars. But one of the things that we've been learning from whether it be gravitational microlensing studies of planets on extremely elongated orbits or planets that are actually not bound to a star, or the interstellar objects that we've been finding in the solar system, such as Oumuamua and Borisov, all of these are telling us that there's a lot of bodies that are just traveling through space, just floating through space. So one of the things that struck me was, well, how close on average is this nearest planet-sized object? Like, say we take an object the size of Mars, how close is that? Is it closer than Proxima Centauri? So we took all the available constraints and then tried to map it out in this paper with Marshall Eubanks and Andreas Hein again. And we found that the nearest planet-sized objects could be almost an order of magnitude closer to Earth than Proxima Centauri. So some of them would be, instead of being 4.2 light years away, would be half a light year away, or 1 light year away. So they could be a lot closer. So this was one of the things where one doesn't really think about it, because we are again taught to think of exoplanets as being around stars. But once we sort of let go of that notion, you turn the crank and then you work out where the closest could be, it turns out to be quite a bit closer potentially based on the available data. And then the follow-up part to that, the engineering part was, well, 0.5 light years is still pretty far. I mean, it's not exactly as far as Proxima, but it's still plenty far. And then the question was, could chemical propulsion get there? And then we looked at it with the current technology. Answer was a resounding no. No matter what kind of orbit maneuvers you do, what kind of slingshots you do. I mean, there might be some super crazy scheme, where you do an endless number of such maneuvers and get there. But insofar as doing 1 or 2 orbit maneuvers and, Jupiter orbit, solar orbit, doing slingshots, none of them were actually getting us there in a reasonable time, which was like 50 years or so. And that's why that doesn't seem very reasonable, 50 years, but Voyager has been traveling for 50 years, still giving us data. So then we had to look at a whole bunch of other propulsion, electric sails, light sail, electric propulsion, nuclear, thermal, nuclear electric, blah, blah, blah. So yeah, that was one work where, it all sprang from thinking about what exactly is a planet and then how close is said planet.
Yeah, and it is kind of exciting. There was a brown dwarf that was discovered fairly recently that had methane emissions. So probably some kind of interaction with a moon. And so when you think about Enceladus or Europa, you've got these tidal interactions between a moon and a gas giant. Well, maybe you get the same thing. So the planet itself might not be habitable, but maybe you have 2 stars, maybe you have a gas giant out there with planets orbiting around it, and they're habitable to some extent.
Yeah. Oh, yeah, definitely. And then the other possibility is you may not have life on the surface, but you may have life underneath the surface, again, just like Europa and Enceladus. And then you could have tidal heating, which might even heat the surface enough that perhaps even surface habitability is possible. So I've actually been spending quite a bit of time over the years on rogue planets. I think the first work we did was in 2019. So it is a bit of a recurring theme, but with every year, of course, we get more data. So we are able to constrain the potential abundance and distances of these rogue planets more and more. And of course, we also start to incorporate more of the engineering factors into consideration, such as how would we explore these worlds on a relatively short time scale of 1 or 2 human generations.
Right, which is always ideal,
right.
For the researchers who start the work to be able to see the results of the research. But, but then also, I mean, they always say like what is it? You want to plant a tree that the wise man plants a tree that he may never be able to sit under its shade, right? That we're so caught up in this fast turnaround time. Oh, we need to be able to make this within 20 years, whatever. But if we're patient, the Voyagers are going to reach the equivalent of the nearest star system in 50,000 years. They just, they weren't pointed in the right direction, and they won't be able to operate for that length of time. And so when you think about those rogue planets coming by, they probably come much closer.
Oh, yeah.
Right?
Oh, yeah, definitely. Yeah, no, the ones we are talking about, do pass within, because as we said, the closest one might be, about zero point 0.5 light years from Earth. So yeah, definitely quite a bit slower. Not too far out. In fact, some of these rogue planets will pass at distances that are comparable or perhaps even slightly smaller than the outer edge of the Oort cloud, which contains the comet. So yeah, they're definitely not close. I mean, they're not far off. They are passing by, relatively speaking, in our neighborhood. I mean, so, which is fun because instead of us having to venture out into all reaches of the galaxy, which right now is a very science fiction-y idea and not, something very realistic. Yeah, we are just waiting for all these objects to come to us and we can just survey them in our backyard, so to speak.
Right. Hitch a ride as they
Right,
continue on to,
right,
to other
right,
locations.
right.
But like just this process of what we're doing, right? We're sitting here and we're brainstorming, we're talking about different ideas. That's one thing, but the next step is to commit to actually writing a paper, to doing the math, to spending however many, you produce 10, 15 papers a year. Each one is a month's work in addition to your teaching and so on. So for you, what crosses that line between you just doing like a back of the envelope calculation with Andreas and and other collaborators, or what's you actually seeing that, okay, fine, this is a paper? How do you draw that line between that?
Yeah, well, I think one of the things that's sort of helps, although it's not always a fail-safe, is the idea of testing your hypothesis or your claim. Of course, to some degree, you can always model anything, but then the other thing one wants to know is there a concrete plan whereby you could further analyze the hypothesis or test the hypothesis ideally or falsify it to use the Popperian metric and so on. So I think that's sort of been, mostly a guiding line that if one speculates, it would have to be rather disciplined speculation that could be subjected to some form of falsification. Now, of course, for some of the more futuristic engineering projects, it's not really about falsification, but in those works, it's more about figuring out, okay, do we have enough of a concrete path? Yes, we do have to hand wave away some of the specifics, such as, say, the geopolitics of putting a 100 megawatt array in some part of the world. Obviously, that those kind of considerations are super important, but one does indeed sweep them under the rug. But some others, we can and do predict certain things, such as saying, okay, for this light sail, this is the optimal trajectory to achieve a certain objective. And then, like we've discussed, perhaps light sails can be scaled up. And so at various points, one can have checkpoints to see their viability. And so circling back to the scientific idea, I've done, of course, a lot of work on trying to understand the habitability of exoplanets and the potential for life on different kinds of exoplanets. Well, for all of those, you can try to identify putative biosignatures or some other geological markers that might manifest. And if so, again, you have a concrete plan for, testing these things and then trying to figure out whether they work. So I think that's been my guideline. So one or two of the work that we did not pursue further did not meet these criteria that I spoke about. So they were just, mostly sort of, there might have been some doodling on, pieces of paper like these, but after that, they never saw the light of day.
That's great. What are you obsessed with right now?
Well, one thing that, this is perhaps the current one, so it has nothing to do with our discussion. One thing that is really taking up a lot of my time and interest is thinking about how small can a living organism get. So that's something that has not been studied a whole lot, but it again turns out to have a lot of real-world implications for astrobiology, because in 1996, there was this meteorite, Allen Hills 84001, and people claimed that, they had found these putative nanofossils, I should call them, microfossils, that were that were found, ostensibly found, and it led to a whole lot of media attention. I believe there was a press release by President Bill Clinton on
Yeah,
the
I
White House
remember.
lawn. Yeah,
Yeah.
so big. I mean, again, I think it was a very interesting paper. It actually kickstarted modern astrobiology. Now we think that it doesn't seem to stand up very well to scrutiny. And there's many reasons why. I mean, many of the non-biological mechanisms can replicate similar patterns and so on. But one of the thing that people bring up is, those microfossils, more accurately nanofossils, are too small to be actually compatible with living systems. But then the question is, how do we know? I mean, and the most simplest answer is people just compare with known bacteria, archaea, and so on Earth. But I think there are ways to approach it from the standpoint of what kind of biochemistry do you need? What kind of biophysical constraint do you have? What kind of metabolic constraint do you have? So lots of different constraints. So that's something that's been of a lot of interest for me lately.
And do you have a sense? I mean, we always sort of talk about viruses. We argue, are viruses life? Are they not life? And then there's whatever is the smallest life form right now, like some kind of archaea or whatever.
Right.
Does it appear that you could miniaturize the smallest life form by a few orders of magnitude and still have it function as life?
Yeah, so that's a very good question. So, my investigation did lead me to write one paper. I think it was in 21 or 22, and then I had one more in 24, so a few months back. But this is, I see this probably as a multi-year program again. So yeah, so therefore, whatever answer I give you is going to be a preliminary one. Now, with that caveat out of the way, and we scientists love our caveats. If we have given the chance, we would just fill the entire sections with caveat. But yeah, now coming back, so the smallest bacteria and archaea that we know of seem to have sizes that are about 100 to 150 nanometers in diameter. So that seems to be about the value that we know of right now empirically. So some of the theoretical work I've done has shown that perhaps the size in terms of the diameter could go down to about 50 nanometers or so, but not a whole lot more. So in other words, it is not too far removed from the absolute minimum we are actually observing on Earth. Now, viruses are, of course, a different story because the requirement you have to build a virus is a lot lesser than having a fully free-living organism that, doesn't have to rely on some form of parasitism or some form of dependency on another organism. So I think, so I would say that the limits that the theoretical models seem to be predicting appear to be quite compatible and close to the limits that we observe on Earth, which again seems to have some interesting implications that perhaps evolution is not something, where the whole space of the parameter space is not being arbitrarily explored. That is to say, you can't have a 1 nanometer bacterium, but rather it is constrained by certain physical and chemical requirements. So I think that has been the one big question that, I've been grappling with over the last couple of years, which is what are the chemical and physical constraints on living systems, and then how could these constraints inform us in the search for life, even life as we don't know it as well.
Oh, that's really interesting. It's kind of a fascinating thing all on its own. It has implications to the work that you're thinking about with the Enceladus probe, but also the search for life, both in extreme environments here on Earth and maybe in other places when you've got other planetary conditions that might have a change to the world. Well, Manasvi, thank you so much for taking the time to chat with me today. I really appreciate it. You, like, as I said, partway, you're sort of one of the most creative but grounded space researchers out there, and I appreciate you taking the time to chat with me today.
Yeah, thank you so much, Fraser. And you've done great work in terms of popularizing so many different aspects of space sciences. And I look forward to following your work in both Universe Today as well as on your channel. Thank you
All
so
right.
much for having
All
me.
right. Thanks a lot. I hope you enjoyed that conversation with Manasvi Lingam. Now, I'm going to chat about sort of my thoughts on the interview, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Dennis Alberti, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Mark Anstis, Modso, Paul Rohrbach, Stephen Kosaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I really can't understate how interesting the list of topics that Manasvi has worked on, and just how wide-ranging they are. And I promise you that if you sort of look through the list, look through the papers, each one of them is catnip to the kinds of people who are interested in this channel. Futuristic propulsion systems, searching for rogue planets, methods of determining astrobiology. There's even Lagrange point papers. It's amazing. And I'm really fascinated by scientists who will do the work that's sort of everyone's expecting, the kinds of papers that are going to get into the kinds of journals, but who are also willing to step outside of that comfort zone to take on ideas that maybe are a little bit out there and yet are scientific questions and are worth thinking through more deeply, putting in the time to do the math, to try and figure out if these ideas are feasible or not. And so, I'm going to put a list of his Google Scholar list of papers, and then I highly recommend you just go through that list and just click on any that strike your fancy, and I'm sure you'll be rabbit holing for several weeks. All right. I hope you enjoyed this interview. I've got lots of other interviews about light sails, about Enceladus, about collecting samples from geysers. So that also should keep you busy. All right, we'll see you next time.